Hi, my name is Liona Fan-Chiang, and you're joining us for week 2 of a review of the New Astronomy, Kepler's New Astronomy book. And we are going to start with book 1, right at the beginning. If you missed the first class, it was going a little bit ahead to see where Kepler ends up, and also really reviewing the philosophy behind why Kepler is doing all of this rigorous work, why he devotes his life to astronomy, and much, much more, as you'll see. So some of you had some fun going through book 1 and doing the homework. And I want to go through some of that because I think it is somewhat revealing. So in book 1 of the New Astronomy, he is starting off with what the situation is as when Kepler comes in. And he actually says he shapes chapter 1 as he does because he wants to show what the basic assumptions are that he is trying to overthrow, and thus setting up the rest of the book. And some of them, for those who have read it, are very funny. To us now, at least, the assumptions are very funny. And maybe they weren't so funny then. Maybe they were fine and dandy, but to us they're very funny now. And so one of the things that he starts with is just basic astronomy. And he points out right at the beginning that the reason that astronomy has brought wonder to people is because the stars do not move uniformly. And if they did, we would not consider investigating them. There would be no question posed. But they don't. They do not move uniformly. And there are many things that strike wonder. One of the things is that, well, the first thing that you see is that the night sky moves all the time, constantly. And you don't really see it. You may look down and think about something else and look back up and say, oh, the stars on the horizon are no longer the same stars as before. So in that sense, you'll put together in your mind that there has been change. Throughout the night, you'll notice, if you stay up even just a couple of hours, that some stars move faster than others, and one not at all. So that's already the first thing that is irregular about the motions. And there are several things that are irregular. I asked people, I'm not sure if I put it in, I think I did. I asked people to make a list if it's helpful. Maybe you just keep it in your mind. For me, it was helpful to make a list of the things that are irregular, because those are the things that are going to drive the whole investigation of astronomy. And these are things that are irregular about the observations of the night sky. And from Earth, that's all you really have. And there are simple things that people take for granted, like how do you tell how far something away is? How far away is the sun, or Mars, or the next star? How far away is something you can't touch? And basically, you can't shoot at or anything like that. You can't interact with it in any way. And distance is something that is so common everyday life, in everyday life, that we don't really think about it. But the type of in this first chapter, he goes through there's several, but probably 4 main irregular motions that are going to make or break your model, basically. So one of the first things that comes up is this first motion, which is what he calls the first motion, which is just this basic motion across the sky around, it seems to be around a point that is singular, that is not moving. It's the only point that's not moving. And we call it the North Star. Now that may be a little revealing. It does point north. So one of the questions was, where would the North Star be if you were at the North Pole? If you follow the North Star all the way to the North Pole, the North Celestial Pole, where would the North Star be? Most people got this one. It would be right above you. You couldn't go any further except up at that point. Anywhere you go around you, if you headed toward the North Star, you would end up in that one spot. So, and the next question was, if you were in Ecuador, where would the star be? And some people were more precise than others. Someone said that if you were in the northern side of Ecuador, it would be on your horizon. If you were on the southern side, you would not see it. So it's named Ecuador because it's on the equator, which is also a little bit funny for people, because most maps we see only include more of the northern part of the map. And we forget that there's a whole continent in the south. Nobody lives there, so it's often not on the map. But it is in the equator really is that low. And at the equator, the North Star is on your horizon. And then the other question then was, okay, knowing that the star at the North Pole, the North Star is right above you, and at the equator it's at the horizon, how do you tell where you are from that? And a few people had something to do with distance, maybe walking to the North Pole. I don't want to walk all the way to the North Pole to figure out where I am first. It was actually some interesting hypotheses, but you can figure out where you are relative to that from having these limits. And then the question is, do you measure it from the zenith, or do you measure it from the horizon? And funnily enough, the latitude, when you look at a map and you see latitudes, that's what those degree marks are. You see the equator is 0 latitude and so on. The degree marks actually measure, they are where you see the North Star above the horizon. So at the equator, it's 0 degrees. At the North Pole, it's 90 degrees, and so on, and negative 90, and so on. So just to give you a sense, the astronomy takes a lot of imagination, and that may have been what you found. It is the case for me. I feel like I have to take some time to tell everybody to shut up and say, look, I gotta think about this for a second and actually imagine motions, because motion is not I think this is why astronomy is one of the first sciences, is because motion is, in this case, is absolutely not sense perceptual. And therefore, all your hypotheses, and even things that are considered sense perceptual, just are not. They occur in the imagination, and you have to be able to make mental experiments and imagine if Earth's day were just a little longer, just a little shorter, or if for problem 2, somebody had considered, what if the Earth actually went around the sun in the opposite direction? How would you know? And those are really good things to ask, because it does get back to, okay, well, why must why should it be one way or the other? So problem 2 addressed a very important aspect of the entire work of the new astronomy, which is the mean sun. And in chapter 1, Kepler brings up this mean sun. Now, what is the mean sun? And that I actually didn't have it. I think maybe somebody had. Oh, here. I asked people to find the mean sun, and I had the quotations "find" because there's really nothing to find. And this is Kepler's big contention with astronomy at the point which he exists. And he says in his chapter summaries, which we'll be reading this week, that when he was talking to Brahe about this mean sun, which I'll come back to what that is, and the mean sun is something that's calculated. It's not the actual sun. He said Brahe had an opposition. He said it worked. Why should I change it? And that this was 4 years ago. So 4 years from when he's writing this, he's already had this debate with people. So what is the mean sun? That's really the question of part 2. And I said basically, if you know what it is, you should be able to calculate it. So a long time ago, the ancients said that, which include everybody up to Kepler basically, said that, okay, the seasons aren't the same length. There are indications that we can get that the sun is not going around us in a uniform way throughout the year, or we are not going around the sun in a uniform way. So at that, really a long time before this, we already knew that the orbit of the sun or the orbit of the Earth, depending on whose model you attributed or you ascribed to, was not uniform. But we didn't know how non-uniform it was, and it was very hard to calculate. It's sort of hard to take a measurement every single day and figure out, what time to wake up. And so they adopted this thing called the mean sun, which is, the orbit is pretty much circular, and it's pretty much even. So let's say it is exactly even and exactly circular. And according to that, where would the sun be? So that's a fine idea for determining time. We basically do it with our time, our clock, our calendars. We assume this is a 24-hour day and so on. And then 24 hours doesn't change every day. If we did, actually, we might have a much more astronomical society. I don't know. But it might be okay for determining time. It is not quite the same for determining how the stars move or how the planets move. But it is the way that the Kepler's predecessors, this mean sun, so this sun that would travel in an equal way constantly, is what Tycho Brahe, Ptolemy, and Copernicus used as their sun, as their actual sun, for their measurements, for their ephemerides, their tables. And of course Kepler said, well, why don't you just use the real sun? And like I mentioned earlier, when Kepler brought that up, Ptolemy said, well, I used the mean sun, it was so much easier, and it works. It works for the first motion, and we'll get to that, what that is. So Kepler sets out to prove, and he states it in this first chapter, and it'll become more clear later throughout book 1. He sets out to prove that there is a reason why you should have something physical that is governing the motions of the planets, the heavens. So problem 2 if you were stumped, as one person said, I'm stumped, you take you just average out the sun's motion throughout the year, through all the days. And then, okay, so that's that. Okay, I'm going to go through the rest of the motions of chapter 1 because although it's not the large, well, it is actually a large part. I think it's very important to get a sense of all the paradoxes that drive things, to put things in context. So, like I said, there's these 4 different motions, and 2 of them are just purely observational, supposedly. So one is this I mentioned, which is this the stars move around all the time. The second one is that as the stars move around every night, there are a few that seem to lag behind, that seem to fall behind. And the funny thing about that is that you saw these in the videos, is that if you just try to take in their motions, if you just try to take in their activity, you get these large spirals, right? They never quite come back to where they were the night before. And that's why they're called the wanderers. But that if you subtract the daily motions, you find out that these wanderers actually travel faster than these other ones. And this is what is called the second motion. Okay, so you have the first motion and the second motion, which are observational. Then you have, well, he says this was actually very important because once you are able to separate these two, which is the motion of the fixed stars and the motion of these wanderers, the planets, then you start to see the real confusion. I like the way that he puts it. He says that actually a couple times. He says all the confusion of this multitude shone forth more obviously. So once you've now separated the motions, now you can see what he calls now the inequalities. So he said that there's a funny thing, which is that the outer planets, Jupiter, Saturn, they do these funny things, which is when the sun comes near them, they go faster. When the sun goes away from them, they slow down, come to a halt. But what do they do first? No, they slow down, come to a halt, and then go backwards, and then come back around again. And so that's another irregularity, right? So that's another irregularity in your observations. And this is only after you're able to separate this first and second motions. After you figured out that there are these wanderers, now you can trace the wandering and find that, oh, they are making these irregular motions. They're going backwards, they're going faster and slower. Then on top of that, so this is the fourth one, I think this is considered the first inequality, even though it's mentioned the second. On top of that, these loops that come around, which are very confusing, are very hard to forecast because they never appear in the same place and they're never quite the same. You know, they're the same size, the same height. They sort of do this sometimes, and then sometimes just do that. Sometimes they make a whole loop, and so on. The spirals are unequal, and that's another one of these inequalities. So these are the things you have to work with. He says these are very important to be able to separate, because otherwise it's just things are just moving. Once you start to separate them, that there are these spirals, the spirals themselves are changing. These spirals I'm referring to what's called retrograde, so it's when they go backwards, retrograde. But that you can figure these out. So one, that they are irregular, but that once you start to separate them, you can figure them out. So that's chapter 1. Just a sort of a setup of what drives astronomy. And one more thing that I'll mention that he brings up in chapter 1 is that there are only, because of all of these, we'll see manifold motions between Earth's own motion, the motion of the planets, and so on, there are actually only a few places where you're looking. If you were to make, for example, if you were to make a sun-centered model, and you wanted to see where a planet was from the standpoint of the sun, there are only a very few places you can do that. And one of them is when you, the Earth, the sun, and the planet are lined up. So you're looking sort of through the sun at the planet. Now the problem is you can't look through the sun, so that one's very hard to use. So the only other one is then when the sun, you, and the planet are lined up in the other way. And he calls this opposition, or achronical, which means just night rising. So this is when the sun and the planet are on opposite sides of you. They're right when one's rising and one's falling, or the other way around. Okay, so the chapter 2 is then I asked people to look at this animation that Jason had made, where Kepler goes through all of the different hypotheses that exist. One of them is a completely Earth-centered system. Another one is where the sun is going around the Earth, but all the planets are going around the sun. And then there's Copernicus's, which is everything is going around the sun, sort of. They're going around the main sun, which is this fictitious point. And he has to make sure that he has to first show that they're all the same, because he wants to disprove them all at once. And well, he wants to adjust them all at once, and not have to go through all of them individually. But also, this it's more revealing because he also wants to show the fact that how they are the same. How is it that all of these different ones that, between an Earth-centered and a Sun-centered, and an Earth-Sun-centered combination, how is it that those could all possibly be the same? Mm-hmm. And this actually, I think, gets at a very important aspect. He brings it up right at the beginning of the book, and it's something to keep in mind, because it brings up a very philosophical aspect of this whole thing. In chapter 2, he has these. He outlines sort of what other people have brought up as physical hypotheses, and you'll see if you sort of keep it in mind, you'll see throughout the chapter he keeps on bringing up this physical. What is actually physically going on? And this is it's not an important concept for people before him. And so the fact that he continues to even try to impose a physical hypothesis on other people's mathematical ones is very important. So he says, before there was this hypothesis from Aristotle that had gone through these different manifestations of these solid orbs, and each planet is, of course, moving in an exact sphere, an exact circle, because the planets, the heavens couldn't possibly do anything else other than be perfect circles that never change, right? They're going exactly at a constant speed. And so in order to have everything going constant, perfect circles, he had everything were standing in these see-through spheres, and the spheres each have a mover that can't be material because the material things are not infinite. They can't exist infinitely, and so therefore there's gods moving these, and there's 52 of them, 456 depending on who you're asking. He says this funny thing, which is that Tycho shatters the orbs, and he's referring to Tycho has this demonstration that the comets would shoot through all the orbs, and so so literally then shattering the orbs. So he said, okay, now if the orbs don't exist, then how do you account for this perfect circular motion? And this is very important because everybody's model right at this point, up to this point, assumes that circular motion is the most perfect, and the heavens can't be anything other than the most perfect, and unchanging. Because if it were changing, of course, then it shouldn't have been the most perfect, right? So, but he actually says, no, in order to be a circle, that you're requiring either the planet to have a soul that is thinking about two things at once, or the orbs, or something else, some combination, where the planet has to look at a center. And for some of these models, the center doesn't have anything. So the center of the circle, it doesn't actually, there's nothing there at the center of the circle. So the planet has to pay attention to a center that doesn't exist and continue to adjust where it is to maintain a distance it can't measure. So whether these other guys thought of these physical hypotheses or not, sort of how it could possibly be done, Kepler was proposing that because he wanted to know what physically is happening. And he said at a certain point, this is absurd. This would give and he's not going to say at this point that the circles should be thrown out, but he basically does. Philosophically, he does. He says this is not physically natural. He goes through a couple of things, as what moves in circular motion and how it's determined. But that's pretty much chapter 2, and I asked people to play with this animation that Jason had. I don't have it pulled up, but it moves through the different hypotheses and look at what happens to Earth's view of the stars when you change to different hypotheses. And you should have found that nothing at all changes. That even if you had a perfect combination of all of them, or if you had if you had a moon-centered universe, that the observations would stay exactly the same. And Kepler proves that with more time and less color. And this is very important, because then if all are right, how do you know which one is right? If they're all the same, how do you know which one is right? And somebody had brought up when we were working that it sort of is reminiscent of the liberal versus conservative problem. And it's you have the equivalence of hypotheses there. So chapter 3, I didn't put a homework problem for this one, but chapter 3 is very important also. He brings up this, they're now trying to resolve this second motion. So like I said, there's a couple of things that everybody introduces in order to sort of resolve these different irregularities. And one of the irregularities is this, this sort of, the planets stop and go backwards and come around. So some people have different hypotheses. One of the hypotheses is just to include an epicycle, a second circle, that's going around a point that doesn't exist, that is going around the Earth. Another one is to accommodate the fact that there is a speeding up and slowing down by moving the whole orbit, the circular orbit, a little bit. So you're just not in the center. And that one he shows in chapter 2. In chapter 3, he's going to bring in something else. And these are building on how other people had thought about this, because these models didn't quite work. So they keep introducing things. One of the things that was introduced by Ptolemy is this thing called equant. And this is a point about which there must be motion that is completely uniform. And they already made all these modifications because obviously from our standpoint, the motions are not completely uniform. And so Ptolemy introduced this point called an equant, about which things are uniform. And that worked pretty well. Although what this is going to lead to, which we'll cover in the next class, is that it doesn't work well enough. And this is very, very important. And it's at this point, which is the resolution of, it's at this point that this whole thing is going to break down. I just want to point one more thing out, is that in chapter 4, Kepler makes this very funny polemic, which is that Copernicus, in order to adjust for both the going backwards motion and the fact that the loops are not equal, he actually introduces 2 epicycles on top of each other. So one circle, and then an epicycle, and another epicycle on top of it. And the reason he does this, instead of just doing what Ptolemy did, which is introducing equant and things like that, is because he thinks he's abhorred by the idea of using anything that's not a circle. And the funny thing is that Kepler points out that by using these 2 epicycles, he actually creates a shape that the planet is going around, which is not circular. And he says Copernicus in his book 5, chapter 4, points out that it's not circular, but goes outside the circular path, and it sort of bulges out. Kepler says, I don't have a problem with that, because Kepler is going to introduce something non-circular, but that his is going to go the opposite. His is actually going to move in. And the other thing, I asked people to read this one paragraph because Kepler summarizes his whole theory in this chapter in a few sentences, which is it starts out, now I, for good reason, will reject as absurd the notion that the moving power should preside over a solid orb, because there are no solid orbs. So, and then he poses his own theory, which I'll let people read. Anyway, I asked people which days are longer? I asked people, what is the exact question? The exact question is, which has more, solar days in a year or sidereal days in a year? And most people said that there were more sidereal days, and a few people said that there were more solar days. This one, I think, it just requires drawing out, and actually, the real question in this question was just, do you know what a sidereal day is? That's actually the question that's being asked. And then if you do know, some of these things will become clear. But so a sidereal day is basically a star day. It's when the same stars come back around. And the solar day is how we determine. Solar day is then when the sun comes back around. So noon, high noon, the sun is directly or not directly above us, depending on where you are on the Earth and what season it is. But with that one, you'll see that it's determined by the fact that the stars are going to be in the same direction always. And so as long as we're rotating around in the same at the same rate, then the star day will be the same. But the sun is not always in the same place. And so you just have to draw that one out. I'm not going to tell you that one. Just one thing to point out is that let's see, is that in chapter 4, Kepler shows that Copernicus's double epicycle is not exactly equivalent. It's equivalent up to 1 minute and 55 seconds. And now the precision of astronomy at that point was only two minutes, so it's just under precision. And he says it's equivalent up to as far as they could measure. There is a fun thing, which is, if you want to know how big a minute is, Jason has this in his animation, which is, so you take a 0.7 millimeter pencil lead and you hold it 8 feet away. That's how much a minute is. Let's just get you a sense of what the precision is. Now our precision right now is actually much higher. I don't know exactly what it is, but I assume that it's much higher than Kepler's time.
How the hell are they going to manage to measure seconds?
Yeah.
Super tiny.
So that's the first 4 chapters, and the next part we'll actually go through the part he's excited about. The 2 chapters are very long, but they are substantial, and you can thank Jason for having done lots of animations for them. And but they're essential because now he's actually going to bring in his hypothesis, and his simple hypothesis is, you're so close to the sun already, why don't you use the real one? And what he has to do, though, he has to prove that using the real one is going to make a big difference. And you would think that philosophically it would make a big difference, that you're not just shaping your whole world around some point that doesn't exist. But for him, he thinks it's important to prove to these academics that it also has to practically make sense. So that'll be the next two chapters. I'm going to stop there and see if people have any questions or comments.
I think it's interesting. He just makes this point about sufficient reason, that you have God is reasonable and has wisdom.
Mm-hmm.
So these, of course, the solar system is going to have to make sense. It's going to be reasonable. Anyway, it's just interesting, and you can see the connection between that and what Leibniz is really fighting against, and what he's doing, and really emphasizing this point that God does not do anything that is not unreasonable. It's not arbitrary. And we can understand that.
Can people hear that? Yeah, okay. Yeah, exactly. He's revealing what, it's a very theological thing. He's revealing what people think about how the universe works, God and creation, just through the way that they impose or what type of axioms they impose on the models, on the astronomical models. Like, for example, that he says at a certain point that Aristotle's God, if he were to believe in it, only exists for the very beginning, where he creates these other gods that then are going to do the same thing forever. We're going to move in a uniform way forever.
On the previous models before Kepler, they were like 2D models, like where they didn't go like with the y-axis, the z-axis kind of deal, like up and down. And did Kepler have that in mind?
Yeah.
So up and down.
Oh yeah. So book 5 is going to go through up and down. Oh, actually no, book 2 is going to go through latitude. And he does do that. I have not looked at it, but Jason says that their models are very weird and have several different cycles on them in order to account for the up and down motion. Have you ever looked at that? No? Yeah, I never looked at it at their latitude models. Yeah. So, oh yeah, right. He described it in the last class, and I sort of understood it, I think, which is, so you have the plane which you're looking at on paper for the longitudes, and then you have other epicycles that are not quite in the same plane. They're tilted, and they may librate, which is they may tilt back and forth. Actually, it would be sort of interesting to see how they accomplished that. Because the other thing is that the loops, like Jason shows that longitudinally the retrogressions are not the same. So some of them take longer, some of them are shorter, and so on. But they also have height differences. So I don't know if these guys ever tried to fit that or not. Oh, I guess part of introducing the equon actually does give an ability to adjust for that, because you adjust how far you are from the planet.
Hey, Liona, could you elaborate a little bit more on?
Yeah.
Which one is Ian?
No, we can't hear him. We can't hear anything.
Can you hear me better now?
Ryan?
Yeah.
I'm muted. I think we're unmuted.
Can't hear you. Are you speaking?
Try it. Yeah.
No, can't hear you.
It's coming up on my screen that he's saying something.
Try talking loud.
Oh.
Can you hear me better now?
Okay, let me mute myself.
Hello? did work last week.
Anyone hear me?
I can hear you.
Can be heard.
I was having some trouble with that fifth question in the homework, and I think partially just because his model was kind of difficult to even see what he was saying it was, but I was wondering if you could just elaborate a little bit more on that question. And also there was something, I don't have the text with me right now, but I remember towards the end of that chapter, or towards the end of the section where he's refuting specifically Aristotle and the Neo-Aristotelians, he says, oh, yeah, I think it's in the paragraph where he talks about Tycho Brahe and how he smashed the orbs, but he also said something about how, you know, Aristotle's model had the orbs on a, since the moving faculty acted on orbs, it was like a blind man without a stick or something, or you know. Anyway, just trying to find it here. Things all backwards, man.
That's in section 8 of part 1, chapter 2. It's 126 in the book.
Oh yeah. He says, Tycho Brahe has demolished the solidity of the orbs, which hitherto was able to serve these moving souls, blind as they were, as walking sticks for finding the appointed road. I didn't really know what that meant, and also just some of the other stuff he was going through on Aristotle's model, like for example this thing about the, you know, how there's now it is quite true, this is on page 125 towards the bottom, now it is quite true that through this solidity of orbs all motions or celestial appearances are so provided for that nothing is left to the province of the presiding movers. Indeed, the whole variety of motions is a consequence of the number and disposition of the orbs, nor is anything else required but that the moving soul receive and retain their activity and be set going from the first moment of creation in whatever direction that is theirs, set forth from their positions, as it were, into space. And it goes on. So I was wondering if you could elaborate on those things.
That turns his off.
Okay. Okay, yeah. That's a good thing to point out. So I brought that up earlier, which is that, so, I mean, this part is the mix between his physical opposition to the orbs and the ontological one, which is, so it says, as long as these orbs exist, so these are solid orbs upon which you sort of imagine a planet is painted on or stuck on it, and as long as the mover, as long as this God's immaterial mover is moving this thing constantly in a uniform motion, the mover and nothing else really has no real control over what is happening with the planet. So that's sort of the very extreme, which is things are completely fixed, and it can't even be it can't be changed by anyone else. So besides that mover somehow disappearing, no other movers can change it, and nothing can be changed ever. Now he says, as long as that exists, then you can sort of explain why things are going in a circular way. Now, if, as Tycho Brahe did, you destroy the orbs, now you have a different problem. Because now there's no structure, there's no solid structure upon which you can say that things are going around in a circle. Now, something else has to be holding it in place. This is why he says, okay, well, does that mean that now there's no orbs, so that means that now it has to concentrate and figure out where, now the planet has to do some thinking, right? Now the planet has to concentrate and figure out where the center of the orb is, and determine its own distance and make sure that its distance is staying still, because it's got to stay in a circle. And there's, okay, now there's a sort of a second absurdity, which is now you're just moving in an ether, and you're still trying to move in circles, but you don't have this walking stick. You don't have this this solid thing that you're just attached to. And so, yeah, neither of those are really resolved by his predecessors. Whether you are traveling orbs, he says Copernicus actually does believe in the orbs, or whether you're just traveling in pure ether. Neither of those really give a physical explanation, according to Kepler. But for Kepler, neither of those really, or both of those give you absurdities about the power and concentration of either an immaterial god or a planet. Does anyone else want to say anything on that?
Well, there was some kind of paradox he was pointing out with Aristotle, talking about mind and body, and you need
Can
a
you turn
soul.
on your audio? I can't hear people for some reason.
Mute yourself.
Can anybody else hear?
Oh wait, I can hear
Oh,
people
it's
now.
working now. Okay.
Okay, I can hear you now.
Okay, well, it just seems very paradoxical that he was breaking down his thought process, because, I mean, he was saying that that each orb has its own mover, and it can't be eternal, because nothing physical can be eternal, I guess because of friction or something. I don't know what he believes, but so it needed to be immaterial, and therefore everything has a mind. And I don't know how all these other autonomous minds of these solid orbs would know how to interact with all these other 40-something odd orbs. But then also he talks about this question of eternity, where he says that that Aristotle doesn't even contemplate the beginning of the universe. So it just seems crazy in a lot of different ways. And that's one thing that stuck out in my mind.
Yeah, and I think it's also important because he is pointing out that this is not just Aristotle. This is still the thought process. This is still the maybe not the model is exactly the same, but some of the basic assumptions are still around.
Hey, I just wanted to read that. You had mentioned the on the physical, on the
Hi.
mode of force. Right. I just wanted to read that quote from Copernicus, where this is Copernicus's only mention of a moving force in his book. He says, because a simple heavenly body cannot be moved by a single sphere non-uniformly. This non-uniformity would have to be caused either by an inconstancy, whether imposed from without or generated from within, in the moving force, or by an alteration in the revolving body. From the alternative, however, the intellect shrinks. So I was really very few people agreed with heliocentrism, but the part of his book that everybody liked was they really liked the double epicycle. That was the biggest impact that Copernicus's book had for many astronomers.
That's funny. You mean they thought the sun was cute, but they liked the double epicycle?
Well, yeah, they didn't like the sun idea. but they were happy to use the double epicycle because they also didn't like the equine.
Oh, they didn't like the equine. Hmm.
No, yeah, Copernicus wasn't the only. I mean, when he said that he thought that the idea is bizarre to him that the heavens should be constant. So if the force changes, or if there was a changing motive power, that would be something that the intellect would shrink away from. He wasn't the only one who thought that. So I don't have any other names for you, but apparently that was the idea of using the double epicycle to get rid of the non-uniform motion of the equine. People thought, oh, that sounds good.
Mm-hmm.
So that was used by other astronomers too, like Tycho. Tycho didn't use the equine. Tycho used the. I don't think Kepler mentions it that much, and at a certain point he just uses the equine after he proves in part 4 that it's basically the same as the double epicycle, except as you said, 2 minutes difference. But I'm pretty sure Tycho also used the double epicycle rather than an equine. So yeah, it caught on.
In order to maintain circularity everywhere.
Circularity and constancy. I mean, each one was circular, but it was inconstant.
Okay. Yeah.
Hey, I had a quick question. Can you hear?
Mm-hmm.
When he talks about when people are observing the planets in relation to the sun along the ecliptic, and that they notice how when the sun gets closer to the planet, it moves faster. I was trying to think about that, and I couldn't come up with really too much of a hypothesis. I was wondering if you know why that's the case.
Yeah, I was
Or
actually.
if anybody else has an idea too.
Yeah, I actually asked Jason this question. That part confused me too. But I think it is just relative to the fact, sort of dealing with the fact that the motion is not regular, and that relative to the fact that when the sun is leaving, when it's not approaching, when it's in opposition, the planet slows down, stops, reverses, comes back and stops, and then starts to move again. Therefore, relative to that, it moves and moves faster.
Yeah, you could also say it's about the second. When Kepler talks about it there, it's about the second inequality.
Mm-hmm.
So he's not talking about the equine. He's not being that sophisticated with that. It's the second inequality aspect of things.
I just want to return to what Ian was saying about that fifth question, because I'm trying to parse in my mind in this difficult section here that we're going through the difference between physical objections and ontological objections. Because I find that he makes, in this section, he seems to make relatively few positive ontological statements. He ridicules Aristotle for the fact that he doesn't believe in the beginning of the world, and he ridicules a follower of Aristotle for claiming to be a Christian, and obviously therefore not being a Christian. But otherwise, he lays out Aristotle's metaphysics without, to my mind, really positively challenging it. Does that make sense? So, from Cusa, I know that Kepler is already aware of the fact that uniform motion is impossible. So I kind of have a sense of Kepler's ontology here.
Mm-hmm.
But anyway, I guess my key question is help me to figure out what I would call the physical objections and what I would call the ontological objections.
Maybe you have something more to say on this, Jason. But I did find that I actually found that some of it was mixed because, obviously the assumptions that Aristotle has or other people have are built into then how the model is made. And you're right, he doesn't say many things that are explicit. Yes, there's one part where he says, well, he doesn't believe in, he must not believe in anything being created because everything is uniform all the time. And the other thing is circular motion, as you said. By this time, I mean, for sure, Kepler doesn't believe in circular motion. He says that very, very explicitly. But that there's nothing that is not, that there's something that's not being generated. I'll just read this, what he says. Where does it say? He says, for I deny that God has created any perpetual non-rectilinear motion that is not ruled by a mind. He says why it would have to be, this is right after the part that Ian was pointing out, but why it would have to have some type of mind in order to do this supposed simple motion of circularity. Yeah, the way I was thinking about it, and may not be exactly right, the right way to use the word ontological, but I was thinking about it as by nature, if the model of Aristotle, if you create a completely different model, a completely different amount of orbs and things like that, still Kepler would disagree by nature because of the basic assumptions that are being applied. That's sort of how I was thinking about it. But those are basically the two places that I saw that, which is this, yeah, the circularity, uniform motion. What are you thinking?
Well, there's this part right here, where after he goes through this whole, it's on page 125, where after he goes through Aristotle's orbs, and then at this end part, he says, nevertheless, it must be kept in mind that the function of the supreme mind is just this, to launch any of the planets in its direction as if into its fixed and proper province. Aristotle, who knew nothing of the world's beginning and did not believe in it, of necessity ascribed the function instead to the governors of the motions, instead of to
himself.
Yeah, instead of to something higher.
Right. And I think it is this question. Who asked this? Is Cameron or Ian or somebody of how do they know what to do? Or how do they interact with each other? How do these minds interact with each other?
Yeah, right. It's totally contradictory.
Yeah.
That helps. That helps a lot. I have another question, which is this Tycho Brahe thing with the comet shattering the orbs. This is, I mean, it seems to me like this must have had a huge impact. Did it? For people?
You have to ask Jason about that one. You know, Jason?
He made a face.
When isn't he making a face?
I heard there was another astronomer that said that there's mechanized windows that open in the orbs to let the comets come through.
Oh, I don't know about this. Jason, want to say something?
You're not sure or something. I'm not even sure that what Tycho thought of that, to be honest.
What Tycho thought of that? I only know because Kepler says it.
Well, Kepler says his response to it.
Say that again?
Nothing.
Okay. Yeah. I mean, Kepler just says in a bracket, Brahe has in fact demonstrated from the trajectories of comets that there are no solid orbs. That'd be fun to look into.
Hey, I had two questions. First question was in chapter 3, where he's shifting what's fixed to what's not fixed, where he changes the eccentric observer versus for the concentric, he's changing the paths. You know what I'm talking about? Like, yeah. Well, I was just wondering that he's saying that it's easier to use the eccentric because all you're changing is the observer. He's talking about the mean sun and the apparent sun, right? That
Yeah, that's what he says.
if you change like the size of the epicycle for the concentric, it changes the path. He's saying that that's the difference between the mean sun and the apparent sun, right? It's
I didn't understand the second half of what you asked.
the mean sun. The mean sun and the apparent sun. That's the difference.
Yeah, that's what he's setting up. As far as I can tell, that's what he's setting up, is that he's about to replace the mean sun with the apparent sun, and so he wants to set up that doing that is going to be equivalent for all the different hypotheses.
Right. Okay. I was just checking. My second question is in part 4, where he's going through the demonstration of the eccentric. He's introducing the equant for the first time. The part where he says that he goes through the thing and is showing how it speeds up and it slows down, and then he says, towards the end of the paragraph, he says that Copernicus rejects it as absurd. What is he rejecting as absurd? That the planets slow down and speed up, or that there's orbs? I'm not sure what he's objecting to.
I'm sorry, where are you? What page are you on?
135, second paragraph.
Okay.
134. The
Oh,
first paragraph.
134.
Yeah, the first paragraph, the last part, the last sentence.
Now fast, now slow. Copernicus, he says, therefore the entire solid orb is now fast, now slow. This Copernicus rejects as absurd.
Yeah.
So Copernicus, who thinks that uniform circular motion is very, very important for perfection in the heavens. Let's see. Yes. Does not like the idea that the orbs are now speeding up and slowing down. And this is in objection to the equant, I think. Yeah. Which is why Copernicus introduces his own double epicycle, 2 epicycles to replace the equant. Does that make sense?
Yeah, he's using the equant, or Ptolemy is using the equant to create equal motion, even though the observations are showing that it's speeding up and slowing down. So it's just like the mathematics of it, but Copernicus is just totally changing it, right? Like
yeah. Copernicus doesn't like the fact that it speeds up and slows down at all.
All right.
We have an offering from Ben on the current precision of observations.
Oh yeah?
Yeah, he says that the ESA's new Gaia spacecraft.
Can you just come over here and read it? Wait, why can't you just say it himself?
Well, I don't know. Anyway, he says that the Gaia spacecraft of the ESA has an observational precision of 7 micro arc seconds, which is 7 millionths of an arc second, which is being able to measure the width of a hair from 1,000 kilometers away.
Wow.
So he said this will allow us to measure the distance and proper motion of 1 billion stars.
Oh.
Yeah.
This is the one that just launched? And
Mhm.
is
Yeah.
neat. Maybe he can include a link to the Gaia spacecraft. I think he actually has a slug on it. Okay, anything else?
Oh yeah. I don't mean to beat a dead horse here, but just something else popped into my mind on this, on what I was originally bringing up, and then what Daniel had brought up there, on this idea of, well, what was the ontological versus the physical objection? Because so I was just thinking about how, in theoretical science, the physical hypothesis is of course shaped by the ontological conceptions which are at your disposal. And so in this case, in the case of astronomy, it seems as if these fundamental ontological conceptions which they had at their disposal were, matter, material bodies, but then also souls. The idea of souls, minds, which can control them. So granting this Aristotle system composed of material bodies in which the planets are embedded, but then also souls which move these material bodies according to however they need to be moved. Because if it were to be admitted, as Aristotle did admit, that the spheres never changed their motion, then that would be implicitly nullifying the need for a soul or a mind to affect that kind of motion, because a mind is not able to affect anything which is not changing.
Mm-hmm.
There's no there's no experience that you could possibly have which is unchanging. There's only changes. And so if these orbs are moving, if you say that it's a contradiction to say that a mind is causing perfectly unchanging motion, because the only time you would need a mind is if the thing slowed down and the god was like, oh look, it's slowing down, I got to speed it up again and get it back to its right speed. All right, oh, it's going too fast, I'm going to slow it down a little bit. But if it's always perfectly moving, you don't need a mind. So it seems like that might be more along the ontological side of it. But then on the physical side of it, they say, okay, well let's get rid of the spheres. Let's get rid of the spheres and then just have the planets moving around these mathematical points. If the mind doesn't have, and you already went through this, but just to elaborate it in my own mind, if the mind doesn't have some sort of reference point which it can use to carry out its function to produce the effect that's desired, right, which is to cause this planet to move in some sort of perfect circle, if it doesn't have any physical reference point to do it, then it couldn't possibly do it. And so then again you're running into a situation where the attempt to intermix these concepts doesn't quite work.
No,
Not if you're speaking like that.
Yeah, I think the ontology there is very much what your idea of a human mind is and what is able to, what determines what a mind does. Because for Aristotle, a mind isn't really something that's changing the universe and what happens in the universe. The mind is something that gets impacted by sense perceptions, and it responds to that. And for him, it's okay to think that something like a soul, for him, the perfect soul is one that keeps doing the same thing forever, never changing. And then also that human ideas don't really have a source; they just there. You would just think things. You can't change what people think. You're just the way you are. And what you have for Kepler is a slightly different idea. And when he's investigating the physical causes, that's also part of the same investigation. One way to think about it is part of the physical causes is what are the causes for what the human mind does, the ideas that the human mind has, and the physical effects that result from those ideas, right? That's one expression of it, and it's very different between Aristotle and Kepler. It comes out later in actually discovering a universal principle. Because there it's very apparent that I don't know if that's helpful for you, but.
I had a couple other things on Tycho. About one funny thing about the comet of 1577 is that Aristotle said the comets were phenomena in the atmosphere, and Tycho proved that wasn't true. That'd be pretty amazing. Anyway, apparently Galileo was an optical artifact in the atmosphere, not actually out in heaven. But on the double epicycles in chapter 4, Tycho did use those. And listen to this quote from Tycho. It sounds almost exactly like Copernicus. He says, this is a letter after Kepler, when he sent the Mysterium Cosmographicum to Tycho, he got some, they had a few letters exchanged. And this is what Tycho wrote him about that. He said, although circular motions in the heavens might, by means of each one balancing curiously, be able to seem sometimes to produce certain angles and various figures and even oblongs by their compounded motion. That is, you put all those epicycles together and you get a path that's not circular. He says, nevertheless, it would be done by accident, and reason shrinks from this supposition. For it is necessary the circuits of stars be compounded wholly from circles. Otherwise, they would not perpetually return into themselves uniformly, and they would frustrate our efforts perpetually.
Did you guys hear that?
Kind of.
Mm-hmm.
Did you have something else? Okay, I think it's a good place to end unless you want to say something else, Jason. Okay. All right, thank you for joining us, and come back in a week, and I'll post the homework by tonight. It should be a link. Hi.
Hi, Courtney.
And I asked people to do it before Tuesday so I can grade them. If you don't get it in by Tuesday at 12, I'll give you partial credit. Turn it in other words. And if you didn't do last week's, do it also.
Or else.
Okay. Bye.
When are you sending out the grades?
I already sent them to you.
Oh, okay. I'm scared.